Today we're going to talk about pump curves and pump selection. And this is an actual image of a family, a suite of pump curve families. So each of those polygons represents numerous curves, and each family is a different kind of pump. We'll talk about how to kind of slice and dice this. I thought that was kind of a cool figure though. Pump curves are notoriously difficult to discern. Continuing our pump week, day 2 in pump week. Today we're going to explain features of a pump characteristic curve. That's what you all just generated in that activity. Pump curve, also known as a pump characteristic curve. We're going to draw a system curve for a pump and pipe system and calculate it. We'll determine the operating conditions of a pump using pump and system curves together, so superimposed together. And then we're going to do an activity where we select an appropriate or optimal pump for a pump pipe system. So we just did this activity with an aquarium pump, and we know that when you turn a pump on, it delivers a certain power. That power output, or P sub O, is calculated as gamma QHP. HP is the height and pressure delivered by the pump. When we did this activity in this little diagram, we just have water coming out, right? And so the pressure is essentially 0 at the outlet. And so we're just recording the elevation. So that's HP component is just elevation in this case. But if the pump were hooked up to an actual pipe system, then we would have that whatever elevation change in addition to the pressure at a particular point in the system. So pumps can deliver elevation and pressure. So as we know, as we raise the tube, what's happening to the flow? Flow decreases, and this is what we measured here. So the flow is decreased as we increase either the pressure that the system has to, the pump has to push through, or the elevation. Because the pump has to raise the water to a higher level, and there's a trade-off between pressure and flow in a pump system. So as we go, eventually we get a flow rate of 0, and that's what is denoted here. So eventually, and it took for this teeny tiny little aquarium pump that we had in our activity, it took 10 feet of elevation to get to 0 flow, also known as the shut-off head. All the pump's energy is just maintaining that pressure or that column of water above it. So here's a very basic pump characteristic curve. At the top, we have the actual pump curve, and this is the relationship between head, which is quantified as elevation, so just elevation head. But again, that could contain pressure head and elevation head, and discharge at the x-axis. Other parts of this curve will include an efficiency curve, and this is just as a percentage. And you can see it's got a different axis, y-axis for it. And that efficiency curve typically peaks in some region in the middle. So often we're trying to select a pump so that we're near the peak efficiency. And all that means is the electricity or the power you're putting into the pump is being used to generate flow and pressure. So you're maximizing your efficiency at this peak, and then there's less efficiency at either end of it. And then brake horsepower, or BHP, is the power that you're putting into the pump. So you can use that number to calculate your energy requirements. And not surprisingly, it increases with flow rate. On the pump curve, we can identify our shutoff head. So we have 0 flow at, in this case, 300 feet. So this pump can raise water 300 feet. Simone's arms are not that long, unfortunately. Brake horsepower is the power provided to the pump by the motor. And when we think about rated capacity, you think of, okay, here's a pump. What flow rate can it give to me? Often a single number is provided. Of course, a pump can deliver a range of flow rates depending on how much pressure or friction it has to overcome. but the rated capacity is typically reported at the peak efficiency. So that's just a number to keep in your head. Definition. We defined this previously, but I'm going to give you another diagram of this. The power consumption of the pump is that's brake horsepower value. It's what electricity you're providing to the pump. There's going to be some efficiency between the motor and the shaft. We define the pump input power as omega t, so the speed, the rotations per time times the torque. We talked about how to calculate the torque. We're not going to do that problem ourselves, but I wanted to define it for you. And essentially the torque is what force at what distance does the motor have to overcome to spin the water at a certain flow rate. And then we have the power output, gamma Q HP. So there's different kinds of efficiencies. We can think of the efficiency of the total system as the power coming in at the motor under the power output. We could also think of the power input at the shaft divided by the power output. But typically, we're just thinking about this total efficiency here. This is basically the electricity over the output. We just generated a pump curve, but here's a little diagram that shows you what we did. You've got a pump at the bottom here, a little aquarium pump. And then we've got different flow rates at different elevations. And so from that video that we saw, this is a very basic way to generate a pump curve. Here is an actual pump testing facility. And so they've got different pumps they can hook up. They can measure the pressure and the flow rate on that system. And basically by shutting a valve off a little bit at a time, you can measure different pressures and different flow rates, right? So that's another way to generate a pump curve. One theoretical way, and this is the conservation of angular momentum equation, is to use this equation, use some aspects of the impeller, the different angles of the vanes and stuff like that, to calculate a theoretical pump curve based on different rotations per minute or different pump speeds. So a single pump can be run at different speeds based on the electricity, the kind of electricity you provide it. I don't exactly know how that works, but I think you can basically change the phase or something about the electricity, the power that you give it, and it can operate at different RPMs. That results in basically a family of pump curves for one pump device. And the family just represents different RPMs. So I've done this calculation. This is basically the torque and the speed to get for different flow rates. So the flow rate is going to influence these two velocity terms. And then this is what generates this kind of theoretical pump curve. So here's an actual pump curve from a real pump, from a real manufacturer. And these are notoriously hard to read. Often you're plotting things by hand. You can probably get the actual data for these in a spreadsheet and then plot your system curve over it. But again, it's got the pump curve family. So that's these black lines right here at different RPMs. We've got the efficiency, which are these dashed lines. Or sorry, it's these contour lines right here. So in this case, you basically have contours of efficiency that work across the different pump curve RPMs. And then we also have our brake horsepower, which is the dashed lines. So all these kind of information is being posted on top of itself. The last curve I didn't talk about is net positive suction head. We'll talk about that next after spring break. That's a calculation you can do with this information to say, okay, at this flow rate, we need, you use this number off of this curve to do a calculation to set the maximum elevation a pump can be above a water supply so that you don't have cavitation inside the pump. So this is just information you get about the pump, and then it's a property of the pump itself. It's basically like what head do you need at the pump inlet to avoid cavitation. So we'll do that whole calculation and after. Let's talk about system curves, and then we'll actually do a system curve calculation. In the video we watched previously, we looked at how a system curve might be generated just from measurements. So at different flow rates, what's the pressure in the system? And that's the pressure essentially that the pump would be pushing against. So this is a flow meter, here's a pressure gauge, and you can create a system curve that way. But we don't necessarily have this kind of equipment or scenarios to run on a system, so we can refer to calculations. So here's a system. We got a reservoir, a pipe, another reservoir, a pump. We have an elevation gain, and then we also have head loss in that system, right? So we can use our energy equation and solve for the head loss and pressure that we have to overcome. So that's ultimately in this kind of open to atmosphere system, one reservoir to another, that's going to be the, the head loss in the system plus the elevation gain. We can use the Hazen-Williams equation, we can use the Darcy-Weisbach equation, and we can say for a given flow rate, what is my head loss with the Darcy-Weisbach, and then what is the overall system curve. You'll note that this system curve has a positive value for 0 cubic feet per second. And why would that be in this particular system? At no flow, there's already some head that the pump has to overcome. In this case, there's this delta Z, right? There's an elevation gradient. So that elevation is the pressure, in feet that the system has to overcome to have no flow rate. So if you were to turn that pump on and it were only sized to provide 120 feet of head, then you'd have 0 flow rate. You would just maintain the reservoir elevations, and flow wouldn't flow backwards back into the other reservoir. So we can think about, well, what flow rate do we need to deliver to this reservoir to ultimately overcome that elevation and the friction head in the system. So we can just do that. It's a very easy spreadsheet calculation. So I just plot the system curve right here. Here's our shutoff elevation or shutoff pressure. So no flow at 120 feet, and then we get this parabolic curve for different flow rates. So that curve then can be plotted over pump curves, and we can figure out based on the RPMs, the efficiencies that we want, the brake horsepower, we can select a different pump and calculate the energy consumption that it'll need. And that's what we'll be doing in just a minute. Let's do a quick example just together on PowerPoint, and then we'll use the worksheet for a different example. So using that same setup, we've got 2 reservoirs. One has an elevation of 100 feet. The other has an elevation of 220 feet. They're connected by a pipe with a diameter of 2 feet. And then we have 12,800 feet of pipe between the two. The Hazen-Williams coefficient is 100. I think that's for like cast iron or something like that. So we'll be given a pump characteristic curve. We'll just say, here's the pump you're going to use. Find the discharge that this pump will provide and the pump head for the system. So here's our pump curve, just something we're going to be given. The next step, the next example that we'll do, we'll have a bunch of pump curves, and we're going to figure out which one we're going to use. And then we can do our pump system curve. So this is just the energy equation that we've written out. We're using the Hazen-Williams equation, which is a function of discharge. So discharge the 1.85 in this case. We plug in our length, our diameter, our Hazen-Williams coefficient. And then we just give it a range of discharges. We don't exactly know what these are going to be yet, but we can just increment them by 5s and see how it goes. So I superimpose, I define the discharge range. That's just an input that I'm going to make. I calculate the head loss using the Hazen-Williams equation. And then I know that I have to overcome, in this case, it's 120 feet. So we start with, at 0, the head loss is 0, but the delta Z is 120. And then now I'm just adding this head loss to 120 feet as we go. So by the time I get to 35 CFS, I have about 300 feet of head loss and then 120 feet of elevation that I need to overcome. So I can plot those two curves together, my system curve and my pump curve. And where they intersect is called the operating condition. This pump could provide a range of flow rates from 0 all the way to probably 40 or something like that CFS. But depending on my system curve, that once you put that pump into the system, then you determine its flow rate, its operating condition. So given that 120 feet, given that 12,000 feet of pipeline and the head loss associated with it, this is where these two nonlinear curves intersect. It's not it'd be really hard to have an analytical solution for this, solving two equations where they intersect, right? So in this case, it's a graphical exercise. So we're going to provide about 20 CFS at about 220 feet of pressure. So you still have some pressure in the system, but also a flow rate. Also known as our match point. So operating flow rate and operating head, operating conditions. Now let's do this exercise together. So take your handouts out. A little bit of a different problem. So now we're going to say, in this condition, we know we need about 70 liters per second to be delivered between two reservoirs. They're 1,000 feet apart or 1,000 meters apart. And there's an elevation gain of 20 meters. So very similar problem as before, just a little bit different parameters. But you can imagine that you say, okay, we need to supply so much flow to the reservoir to meet demand, average daily demand or something like that. We're going to use a steel pipe with a diameter of 0.2 meters. So these are conditions. This is the existing system we have. We want to pick out a pump to do this. So right now, the first figure we have in our handout is this family of curves. 1, 2, 3, 4. Each of these Roman numerals represent one pump, and then the kind of span of curves represents the different RPMs that pump can operate on. So the first part of this then is to figure out, well, which pump are we going to use? And then we can figure out which RPM, etc. So now what I want you to do is to calculate the system curve and draw this over your pump curves. And just do that for one flow rate. Then we'll actually do for different flow rates and figure out exactly where we fall on the pump curves. So let's go ahead and do that, and I'll have you guys work on that. And I'll pause this. So we're going to calculate the head loss at 70 liters per second, which is 0.07 cubic meters per second. We'll use the Hazen-Williams equation. So we had a length of 1,000 meters. Is that right? Okay. And that's going to be divided by our diameter, which is 0.2. All right, raised to the 4.87 times our Hazen-Williams coefficient, we said was 100. Did we say it was 100? It was 100 before. What is commercial steel? 125? 145? Okay. So commercial steel was a Hazen-Williams coefficient of 145. And then our flow rate 0.07 raised to 1.85. So what is our head loss due to friction? Okay, so our head loss due to friction is about, we'll just say 9 meters using the Hazen-Williams equation. And then we have, we had to overcome, let's see here, 20 meters of elevation, right? So our system curve is going to be equal to head loss due to friction. We could incorporate minor losses if we wanted to, plus delta Z. And so it's going to be 9 meters plus 20 meters. Okay, well, Darcy-Weisbach gives us 9 meters, or sorry, the Hazen-Williams equation gives us 9 meters. If you look at the example in the book, which is, this is example 5.11. They did the Darcy-Weisbach calculation and they got that head loss was equal to 20 meters. So we're gonna run with that number. And we're gonna say that for 70 liters per minute or per second, our H system is going to be equal to 20 meters of head loss plus 20 meters of elevation, which is about 40 meters. So let's jump back into our PowerPoint presentation and kind of look at the rest of the process there. So we'll plot that point on this curve to figure out which pump makes the most sense or which pump family. And then we'll figure out what our actual flow rate, operating pressure, rate horsepower, and efficiency will be. So there's 40 meters, and then there's 70 liters per second. So that's going to put us in either pump family 2 or 3. We'll note that 3 kind of overlaps right there. So pump 2 or pump 3, and those are the curves that we have. But now we need to actually figure out, well, what RPM and kind of efficiency makes the most sense. So we can use, we'll stick with Darcy-Weisbach, and we'll plot the system curve for different flow rates, spanning the flow rate that we want to have. We're not going to be exactly on 70, but we want to be at least 70, right? So we'll plot the system curve for 3 different flow rates. We'll plot that over these 2 pump curves and we'll figure out which match point is going to make the most sense. So I did that right here for 60, 70, and 80 liters per second. We'll use the Darcy-Weisbach equation to get these values for our system curve. So just delta Z plus the friction loss. And then why don't you guys draw these out? So we'll take these values and then draw them out on those 2 system curves and actually draw the curve yourself. Okay, so if we draw those values out on these 2 pump curves, so 60, 70, 80 liters per second, 35, 40, and 45 meters of pressure, then we can start to figure out which of these pumps is going to make the most sense at which RPM. So we'll connect those dots. And what we can do is read out the various efficiencies, because that's what we're going to be interested in, as well as flow rates for this. So here's where the pump curves intersect. We can look at these 2 different RPMs. We'll just kind of focus on pump 2 right now. So this curve crosses, the system curve, which is in red, crosses the pump curve at 385 RPM. This is going to be a little bit below 70, so that's not going to work. We can look at 4350 RPM, and that's going to be just above 70 liters per second. So that's going to work. And then we can come over here and figure out, well, we've got for pump 3, we've got 2 different RPMs that'll work for us. One is if this is so 40, 60, 80. So this is going to be right around 70 liters per second. And then at this higher RPM, so 40, 50 RPM, we're looking at maybe 75 liters per second, something like that, with these various pressure heads. We know that we have at least 20 meters that we have to overcome. And then I guess our system curve accounts for the pressure and the elevation difference. So here's some options. I think we basically have under pump 2 operating at 40, 50 RPM, and then pump 3 operating at these 2 different RPMs would meet our flow rate requirements. But some other things to think about: what's the efficiency? So at this match point, we have a 52% efficiency. At this match point, we have 59 and 58 efficiency. But then on top of that, so a higher efficiency sounds good, but that's based on what energy input to the pump. So 52% efficiency at 71 horsepowers. And note that I draw this line down and we just find where it intersects, and then we come across to this, we come across to this axis. So I come down, I say, what RPM am I operating at? And then I come across and look at the horsepower input. So it's a different axis, right? So then I can use these efficiencies and the horsepower, the brake horsepower, which is the energy input into the pump, to figure out what are my energy costs going to be at these different operating conditions. So here's the summary of that. And I can multiply these out and figure out then what energy requirement is going to be the most. And if you want to do those calculations real quick, maybe tell me what you think the biggest or the least power consumption will be under these different operating conditions. So the efficiency is interesting, but ultimately we're looking at the power input, because that's going to tell us how much power the pump's going to require. And so we're probably going to think, well, if we can get 70 liters per second at 71 horsepower, you can convert that to kilowatt hours, right? By horsepower is kilowatts, and then you think about the hours in a day, and you get kilowatt hours. So, and that's what we base our electricity consumption off of. So we're probably going to choose pump 2 because it's using the least amount of energy to get at least 70 liters per second. So we'll run with pump 2, and it's giving us right about 70 liters per second. And then the last thing we'll talk about is net positive suction head. This is another thing we can get off of this graph. And we can read that off for this curve, which gives us about 3.5 meters of net positive suction head. That's something to write down. And then in a subsequent lecture, we'll cover how we use that. But that's going to be a number we use to design our pump system. Great. To summarize, we learned about pump characteristic curves. And this is a curve that shows the relationship between flow and the pressure supplied by the pump. HP is equal to Z plus whatever friction we have in the system. Or sorry, that's the system curve, plus whatever pressure we have in the system. And it looks like this, and you're going to have a family of curves based on different RPMs. And then we also have our system curve. And that is based on the pipe system. So maybe you have a water tower and a pump supplies that water tower from a reservoir. And we calculate that system curve. This is a relationship between flow rate energy loss in the pipe system and elevation. So writing the energy equation out, we can calculate the system curve as the head loss due to friction. We could incorporate minor losses too, so I'll just make that generic, plus whatever elevation we have to overcome. And we can use that, we can essentially create a system curve by designating flow rates, calculating the head loss due to friction in the system, and then getting the total system curve, which is delta Z plus our head loss. Finally, we can select a pump and determine operating conditions. By superimposing these two curves. So if we go back to our pump curve, we can plot our system curve over it. We can figure out what's this flow rate that we need. So maybe it's a range of flow rates. So this would be Q design. And then where your system curve intersects the pump curve, we get our operating conditions. And we call that the match point. Say we have multiple different types of pumps that could meet these operating conditions or the design conditions that we need, then we would choose the pump that requires the least energy. Right. So next time we'll talk about what happens when we put more than one pump together, pumps in series and pumps in parallel, and what that does to the pump curve and what that does to our operating conditions.